So in this segment, we're going to discuss the theory of plate tectonics, and we're also going to go over some key elements of that theory, namely the different plate boundaries we find on Earth. So the theory of plate tectonics has its origins in the theory of continental drift, and as most of you know, that theory was developed by Alfred Wegener, who was actually a meteorologist. Rather than a geoscientist. And his idea was basically that all of the continents on Earth, or at least most of them, used to make up a supercontinent, one large continent called Pangaea. But at some point in the geologic past, this continent broke up into the current continents and sort of drifted to their current positions, hence the name continental drift. And he had a few reasons for believing this. As you can see on the diagram to the right here, he noted that there's evidence of glaciation across all of these southern continents, what we call Gondwana today, where it didn't really make sense for them, all to be glaciated at the same time if they were where they currently are in the past. He also noticed that certain fossil assemblages were common across different continents where, for animals that, could not fly or swim and could not easily get between these continents. So they must have been either connected or in very close proximity. As you can see on the diagram, different sort of rock deposits sort of correlated with one another across continents in a general sense. And lastly, the shape of continents almost seem to fit together like a puzzle piece in some cases. The notable example being here between South America and Africa. So for all these things, this was too much of a coincidence to Wegener, and he believed that at some point in the past, all the continents were together. The problem was, and the reason why his theory was never taken seriously at the time, was that he didn't provide a mechanism that could have moved these massive continents apart from one another and broken up this big supercontinent. He posited, things, he's a meteorologist, so he posited things like tides and other sort of, astronomical type phenomenon, but these just simply didn't have the energy needed to move giant land masses. So at the time, his theory wasn't taken seriously. So we're going to fast forward to the early 1950s, and around this time, people are starting to use technology from World War II to map out the seafloor. And it was in 1953 that a geoscientist named Marie Tharp was looking at some sonar records for the Atlantic Ocean and discovered the Mid-Atlantic Ridge, one of Earth's, I believe, Earth's longest mountain range, but nobody knew about it until she discovered it in 1953 because it's under 4 kilometers of water. And from this, there was lots of people involved in the development of these theories, but the big name here is Harold Hess used these findings and others to develop the theory of seafloor spreading, the idea that new crust is being created at these big mid-ocean ridges, like the Mid-Atlantic Ridge, and spreading outward and eventually sort of being recycled in these subduction zones sort of near the continental margins. And another interesting finding came a few years later in 1963 when a few scientists, Fine, Matthews, and Morley, all discovered around the same time that the Atlantic seabed had these magnetic stripes on it. So when certain minerals, say for example magnetite, are deposited, they align themselves according to the Earth's magnetic field. But what we found out since then is that the magnetic field on Earth occasionally flips, every several hundred thousand of years. And this flipping is actually recorded in the sea floor. And we noticed that the areas immediately around the mid-Atlantic ridge have a normal polarity like they are today, but if you go further out and sort of mirror images on either side, you can see zones of reverse polarity, normal polarity again, and so on and so forth. This is an oversimplified diagram. Not all flips last for the same length of time, but you get the idea that this provides evidence that this is a process happening over geologic time as indicated by the different polarities. But seafloor spreading still didn't provide a mechanism for how plates move, especially the big continental plates. And this would require further refinement over time. Firstly, developing the idea through seismic records and theory that we have, of course, the surface of the Earth is a solid lithosphere, but as we know from one of the previous modules, it rests on sort of this plastic structural layer, the uppermost mantle, or the asthenosphere. And this allows for the very slow movement of plates around the Earth through mantle convection. Additionally, for oceanic plates, which are I believe move a bit faster than the continental ones, or at least are recycled, their movement is enhanced by this idea of ridge push and slab pull, where at the ridges, the light buoyant magma is raising up the crust, and then gravity wants to bring it back down, so it sort of slides along, and then in the subduction zones, as plates get older and cool, they become denser and eventually sink down into the Earth's mantle. So these gravity effects also help move at least the oceanic plates along. And other refinements to the theory have happened too over the years. Especially of note are those by John Tusa Wilson, made several contributions to the theory of plate tectonics, including the idea of transform boundaries, which we'll discuss later, as well as the Wilson cycle, this idea that supercontinents sort of, form and break up on sort of the time scale of hundreds of millions of years. So there have been multiple supercontinents in Earth's past, including Pangaea, Rodinia, and several others before that. So now we're going to go over the different types of plate boundaries, and we'll start with this divergent boundary, those mid-ocean ridges that we were talking about. And again, there's this idea that magma is, it's not as dense as the surrounding rock, it's rising. The crust is thinner, so it allows for this rising. And if we remember back to our magma thing, thinner crust means less pressure, which allows for the creation of magma in the first place. But in any event, it's rising, creating new crust at the margin. And again, that ridge push idea, it's falling down due to gravity, moving it out of the way, allowing for the creation of more crust, and the cycle continues. And so there's a lot of volcanism in these places. For example, where these places are above the Earth's surface, like in Iceland, tons of volcanism there. And these types of boundaries, they can also be at the surface in places like the East African Rift Valley, or near the surface, like in the Red Sea. So these are not just exclusively things found in the middle of the ocean. We should also note now the differences between oceanic and continental crust. So oceanic crust, as we know, it subducts beneath continental crust. It's forced underneath. And This is because it is denser than the continental crust, because its chemical composition is different. It's made primarily of silicon and magnesium, and that means magnesium is a heavier element than aluminum, so it'll sink below, especially as the oceanic crust moves further away from the mid-ocean ridge. It gets older, it gets denser, so especially that older crust will tend to subduct because it does become denser over time. Now, that said, older is always relative, and oceanic crust is at oldest near the subduction zone only about 150 to 200 million years old, which compared to continental crust, where we've discovered rocks that are 4 billion years old and mineral grains that are even older, its oceanic crust is quite young. It gets recycled roughly every 200 million years. Continental crust, however, is less dense. It's more rich in aluminum, and as a result, it'll float above the oceanic crust. It doesn't really get subducted or recycled, and it just sort of accumulates without being lost. So now on to convergent boundaries. This is where two plates come together, and there are two types of convergent boundaries. We have those subduction boundaries, those continent-ocean boundaries that we were discussing earlier. These are sites of volcanism because these oceanic plates, which is the one on the left, should be a bit thinner in the diagram, but they'll actually, not only are they subducting and thus being heated by the crust, but we also, when we talked about magma, we talked about volatiles, and they actually bring down a lot of water with them. So between the extra heating from the mantle and the water, they will, sort of heat up and also heat up the mantle rock around them, producing magma. It'll rise to the surface and often create a chain of volcanoes, on the continental plate opposite the subduction zone. So if you think of like the Andes Mountains or many of the volcanoes in the Pacific Ring of Fire in general, it's this process here at work. Another unique feature of these boundaries is this Wadati-Benioff zone, excuse my pronunciation, but this idea that, you have this 2D plane of earthquake epicenters where the closer you are to the actual plate boundary at the surface, the shallower your earthquake will be, and the further you move sort of into the zone of the continental plate, the deeper your earthquake will be. So this is just sort of the contact between the two plates, and you can sort of visualize this contact in 3D space if you collect enough earthquake epicenter data. The other type of convergent boundary, of course, is the continent-continent boundary, and these are our real centers of mountain building. Remember that continental plates are not very dense, so they won't sink into the earth. Instead, they get, bunched up and built up into mountain ranges like the Himalayas, or the Canadian shield would have been formed in a very similar process, just that, since then it's been eroded down quite a bit. The last type is the transform boundary, and these are sort of the ones that fit the other types of boundaries together. So in order for the whole system to work, there has to be, something connecting sort of the disconnected, convergent or divergent plate boundaries. And, this happens in the form of a transform boundary where the two plates will slide by each other without necessarily diverging or converging with each other. And a good example of this is this picture on the left here, which is the San Andreas Fault in California, which is between the Pacific Plate and the North American. But of particular note here is that both plates at this boundary are actually moving in the same direction. They're both moving generally to the northwest. However, the Pacific plate's actually moving a bit faster than the North American plate. So in a relative sense, the Pacific plate here is moving up and the North American's moving down, but they're both moving to the northwest. It's just that the Pacific plate's moving faster, so it produces the boundary there. So that was a quick overview of the theory of plate tectonics, as well as different types of plate boundaries that we find on Earth.